I would like to carry this concept of coherence even further by going a little bit beyond the cardiovascular measures. And so let's revisit this core concept. And we have this distinguishing factor between self, our integrated internal experience, and the external not self. And maintaining the boundary between these, represented by the circle, is critical for the coherent identity. And non-REM sleep, specifically slow wave sleep, with its parasympathetic dominance and stable coherent activity, plays a key role. But it also fosters whole body coherence, an internally focused state essential for reinforcing the sense of self. And it's not just theoretical, it is mediated by well described neuronal central nervous sense CNS processes. And the hallmark of non-REM deep sleep is the slow oscillation visible here in the EEG. This is a rhythm that is often less than 1 hertz, originating from interactions within the thalamocortical cortex network depicted here. And critically, these slow oscillations involve virtually every cortical region, behaving like a traveling wave, especially prominent in the frontal areas. Each oscillation has an up state of neuronal firing and a down state of silence. And so this synchronized rhythmic activity across the cortex, driven from within, isolates the brain from external sensory input, promoting internal processing. And if you go very in deeper at the cellular level, the key component for that slow wave are these T-type calcium channels shown here. They are crucial for this slow oscillation. And these channels have a unique property. They're normally inactive at resting membrane potential, and they only become ready to open or de-inactivated after a period of hyperpolarization, provided, for instance, by the GABAergic input, maybe from the VLPO. Then a small depolarization triggers them to open, causing a calcium influx. And this generates a low threshold spike, often leading to a burst of action potentials. And these cyclic activity of T-type channels, inactivation, inactivation, activation, and burst firing generates the intrinsic rhythmicity within the thalamocortical neurons that underlies the slow oscillations, driving the internal focus of non-REM. And so these oscillations is what gates external sensory perception and enables the organisms to focus entirely within oneself. And this slide illustrates a key characteristic of slow wave non-REM sleep, a significant withdrawal from the environment. And this was the study that was done on unfortunate rats who received a brief laser pulse to the paw, which is normally, painful and aversive. And the recordings show muscle activity, EMG, and brain activity after the laser pulse in both wake and slow wave states. And you can see during the wakefulness, the laser pulse elicits a strong, widespread response with muscle contractions in multiple limbs, as well as the back. However, during slow wave sleep on the right, this same stimulus produces virtually no response in the limbs or the back. So this contrast highlights the fundamental difference in sensory processing responsiveness during slow wave sleep. The brain is not simply turned off, it's actively gating sensory input. And so this withdrawal is a defining feature of non-REM sleep, allowing for restorative processes to occur. The other important point is that these slow wave oscillations involving the T-type calcium channels requires time. And so the initial hyperpolarization, which then de-inactivates these hypercalcium channels, requires a lot of time and also absence of any stimulus into the thalamus. And so this slide sort of highlights the crucial role of the reduced sympathetic nervous system activity and specifically the impact of norepinephrine from the locus coeruleus on slow wave sleep. And so for deep restorative non-N3 sleep to occur, the SNS, the sympathetic nervous system, needs to be quiet. And this data, which was published in Journal Neurophysiology in 1993, shows intracellular recording from a thalamocortical neuron, along with electrical recordings of the cortex. And you notice the slow oscillations of slow wave sleep. And the key point here is that the small labeled section LC represents the locus coeruleus. And when you have brief electrical stimulation of this site, this causes release of norepinephrine in the brain. And this stimulation causes disruption of the slow wave oscillations. And this demonstrates that even a brief increase in norepinephrine, mimicking increasing SNS activity, can interrupt deep synchronized activity that defines restorative N3 sleep. And this is why creating an environment with low sympathetic tone, reducing stress, minimizing arousing stimuli is so critical for achieving high quality, slow wave sleep. So to optimize sleep, we know from our previous discussions from neurovisceral integration model that there's top-down methods to tap down active ANS centers. And this might entail meditation, slow breathing, etc. And plus, to add to this, if my hypothesis is correct, then the type of activity that allows you to orient into yourself would be the most effective because it establishes the internal synchrony and coherence that best recapitulates deep sleep. So I would hypothesize that meditation with an inward focus will likely work to get you faster to reach N3 deep sleep. But this is obviously an hypothesis that I encourage you all to test out. So while I discuss the internal focus and stability of individual systems during non-REM, it's also important to broaden this concept to the idea of whole body synchrony. And this figure shows data across a night of sleep. In panel A is the hypnogram. Panel B is the delta power, the EEG hallmark of slow wave sleep. And panel C shows the high frequency heart rate variability, our marker of parasympathetic activity. And notice sort of the striking correspondence as delta power increases during non-REM, high frequency HRV also increases. And so this demonstrates brain heart coupling, a synchronized fluctuation of brain activity and cardiac autonomic control, reflecting a unified, internally coherent state during non-REM sleep. And this synchrony extends beyond the heart, and it also encompasses brain blood flow. And this study used fMRI or MREG, and this compares wakefulness on the left and non-REM sleep on the right. And we see sort of a dramatic change during non-REM sleep. There is a significant increase in the low frequency pulsations throughout the brain, which indicate increasing blood flow, as shown in MREG data, and particularly in the spectral plot below. And these hemodynamic oscillations around zero 0.1 hertz and 0.2 hertz are synchronized with the EEG slow wave oscillations. So there's coordinated slowing and strengthening of both the neural and the vascular rhythms, suggesting a highly integrated physiological state during non-REM. And it is suggested that this coordination between the nerves and the vessels may promote CSF convection and waste clearance, i.e. the lymphatics. And this internal synchrony during non-REM is not just within individual systems, it extends across brain regions too, crucially supporting memory consolidation. So this schematic illustrates the precisely timed interplay of three brain areas: slow waves originating in the cortex, sleep spindles within the in the thalamus, and the hippocampal ripples also basically from the hippocampus. And notice how these events aren't random, they're temporally coordinated. Hippocampal ripples associated with memory replay tend to occur during the upstate of the slow wave and often coincide with the sleep spindles. And so there's this temporal coordination across different frequencies regions as proposed as a substrate that transfers information across the brain. So in summary, non-REM slow wave sleep plays a critical role in reestablishing self. And we've seen how it creates sort of a highly synchronized, coherent internal state characterized by parasympathetic dominance, stable autonomic function, and coordinated brain and whole body activity. And this closed state is largely unresponsive to external stimuli, allowing for focused internal processing. This allows downscaling of irrelevant synaptic connections, and it establishes a strong detoxification state, removing metabolic waste. All these processes occurring during a unique physiological state, which I say is reinforcing that coherent integrated sense of self.